Hello guys, welcome to my video. This is a very special edition where we're going to be talking about two special kind of variables. Welcome to my video. In this video, I'm going to be talking about a very special topic of scalars and vectors. Scalar quantities and vector quantities are things that you're expected to know as an AS level student. So in this video, in my video series on physical quantities and units, I'm going to first start off by giving you some context on what are scalars and what are vectors. And after that, we're going to move on to solving specific questions from past papers surrounding scalars and vectors. So first, I would highly recommend that you watch this video throughout so that you understand what are scalars, what are vectors, before you go to the videos that I've solved for specific past papers where they've asked us to talk of scalars and where they've asked us to talk of vectors. So please stay along and watch so that you can really be able to understand what are scalars and what are vectors and how we can be able to think of them. So the first one that I would really like to talk of is scalar quantities. Okay, so scalar quantities. Okay, so scalar quantities. Right, so scalar quantities basically refers to a quantity, right? Basically refers to a quantity, right? It's a quantity that consists, okay, that consists of a numerical, okay, a numerical magnitude only. So it's a numerical magnitude, right? A numerical magnitude only, right? A numerical magnitude only. And what is a vector quantity? Let's just talk about them now and then explain later. A vector quantity, okay, a vector quantity is basically going to be a quantity, right? A quantity, right? What does it do? It's a quantity that consists, okay, that consists of both a numerical magnitude, okay, a numerical magnitude and direction, right? So it's a numerical magnitude and direction. Okay, so emphasis being on the numerical magnitude, okay, so this numerical magnitude as well as the direction. But the emphasis for scalar quantities is only on this numerical magnitude aspect only, right? We don't care about the direction, right? We just care about the magnitude. So that's the difference between scalar quantities and vector quantities. In scalar quantities, we're only interested of the numerical magnitude only. We don't care about the direction. But in vector quantities, we're really interested in the direction in which something is acting. I give you some examples explaining how this is going to look like. So we're going to have a table. So we're going to first start off with scalar, right? Scalar quantities, okay? And then on this other side, we're going to have vector quantities, okay? Vector quantities, right? And then we're going to explain how one is a scalar and one is a vector. Examples of scalar quantities, we're going to first start off with mass, right? For example, if a person with Rob, for example, Rob stands on a measuring, on a balance, right? And the balance reads 20 kilograms. Rob weighs 20 kilograms. You're going to ask, Rob, you weigh 20 kilograms in what direction? You're never going to ask that because there is no direction involved in scalars, right? You don't care about direction. You just want to know the quantity, the magnitude, and the unit, right? You only care about the magnitude only, and no direction is involved. What else do we have? We have time. You have a clock reading 2 o'clock and you ask 2 o'clock in what direction? It doesn't make sense, right? Or 20 seconds in what direction? It doesn't make sense because we don't care about a direction when we talk of time, right? The third one that we're going to have is distance, right? You're going to move from point A. For example, your person moving from point A to point B. You don't care about the direction. As long as you've moved a certain distance, that's just going to be that, right? We also have things like density, right? The amount of substance per unit volume. It's not going to be like kgs per cubic meter, mass over volume. That density is not going to have a specific direction. We have things like area. We have a lot of quantities. We have things like power. We have things like work done. A lot of quantities, really. We have things like work done. We have things like temperature. Everything that if you always ask yourself, can you have a direction in temperature? Can you say 2 degrees Celsius to the left? And if you can't, it's definitely going to be a scalar quantity. Then the other one that we're going to talk about here on vector quantities, we have, for example, displacement. Okay, displacement. You have moved from point A to point B. We can ask, let's say there's a well that is at point at a certain point and you are at point A, the well is your destination, it's going to be point B. If you move in a wriggly line up until you reach your destination, so you're at this point and you just move like this, then you reach your well, right? So basically, that is your distance. What you have traveled here is going to be your distance. But your displacement, what we're going to do, we're just going to take this point and connect it to the other point. The shortest distance that you have moved, that is going to be your displacement, and it's going to have a specific direction. For example, if I'm to connect my compass over here, right, something like this, I could say this is east, this is north, this is south, and then this is west. This is somewhere around a little bit of northeast, right? But the idea how it comes with, then you can usually say that this person has moved a certain meters, 10 meters due northeast, right? The direction aspect has to come out whenever we talk of displacement. What are the other quantities that also involve direction? We have force, also involves direction. Number 3, we have acceleration, right? The rate of change of velocity also involves direction. And then we also have velocity itself. You can say 20 meters to the left, 30 meters to the right. Like in displacement, I could say, you move 10 meters to the left. Rob, move 10 meters to the left, right? That's displacement because you have moved a certain value to the left. Or it could be momentum, right? Momentum, mass times acceleration. Momentum has a direction because it can be resolved. Or it could be, what else do we have? We have weight, right? Again, weight is also a vector because it has a specific direction, because weight can be resolved. So basically, that's what you should be thinking about when you talk of scalar quantities and when you talk of vector quantities. Does this have direction? If it has direction, it's basically going to be a vector quantity. Another important aspect is going to be numerical addition of vectors and scalars. So that's something that we really need to talk about. So let's first start with addition of scalars, right? Addition of scalars. So the addition of scalars is basically, let's say you have 20 kgs, you're just going to say plus 20 kgs and you're just going to get 40 kgs, right? So when you're adding scalars or subtracting scalars or just doing algebra with scalars, for example, you have 20 kgs times 20 kgs, you're just going to get 400 kgs, right? We just do it the normal way that you're used to. But whenever we have vectors, it's going to be a little bit different, right? Not that much, but it's just going to be a little bit different. For example, addition of vectors. So whenever we talk of vectors, we're going to therefore combine with the last aspect of vector resolution. But most of vector resolution, we're going to really talk about it in specific question papers. But for now, we're just going to talk about vector resolution. And if you look at my other videos where I'll be talking of specific question papers, I'll also be talking about the method of parallelogram to solve specific vector problems. But for now, I'm just going to talk about a little bit low-key about the addition of vectors. Okay, so vectors are represented in a certain notation that you're expected to know. So vectors are basically represented by, they're represented by a directed line segment. So they're represented by a directed line segment. That is what represents a vector. It has to be a directed line segment. It could be something like this, okay, something like this. This representing the direction, right? So this represents the direction, and at times, right? So this represents the direction, and at times the length of the arrow, at times the length of arrow, right, will represent the magnitude of the vector itself. Sometimes, but not all the time, right? Will represent the magnitude of the vector itself, right? So this is very important for you to know. The length of the arrow represents the magnitude. The direction, the arrow where it's pointing, represents the direction. So again, it can also be like this, right? Something like this. Again, the arrow is still there, and the length of the arrow is going to represent the magnitude of that vector. Very important. But whenever we talk of vector addition, vectors can be parallel, right? Meaning that they are on the same plane, right? For example, this vector, which is, let's say, 4 newtons, right? Something like this. This is 4 newtons, and then we have something like this, which is 3 newtons, and we've been asked to find the resultant vector. A resultant vector is basically what you expect, the result that you get after you have combined the effect. It's the combined effect of 2 vectors. So the result that you get after you've combined the effect of 2 vectors. For example, if you have 4 newtons and 3 newtons, if you add them up, what you're going to get? You're going to get 7 newtons. So you're going to get 7 newtons to the right. That's basically how vector addition works. You just add them up, then you're going to get one vector that's going to be combined. Okay, and then you could have something that looks like this. For example, you have a vector in this direction, which is like 3 newtons. Then you have another vector in this direction, which is like 2 newtons. So they're going to add up again. So they're going to fight, and this 3 newtons is going to win. And it's going to win with 1 newton again to the right. Okay. Then the last part that we're going to talk about is what we call the head to tail method. It's a method that you're going to apply a lot when you're dealing with vector questions. So it's the head, okay, the head to tail method, which says that you always connect the head to tail, and then you can find the resultant vector by using this method. How does it work? So I give you an example. Imagine you have Sarah who is at point A. Now Sarah has two options. She can visit, let's just say Precious's house, which is over there at point B, right? And then go to the well. So they're gonna, she's gonna move down. Then she's gonna reach Precious's house. They're gonna have some talks, right? It's gonna discuss some issues, and they're gonna have a dialogue basically. And then Sarah is gonna continue with her journey to reach the well, right? So she has taken a very long route, right? She's taken the well, then she's gone and taken the route to go to Precious's house. Then she has reached the well. Or she could have taken one route B, which is just like going straight from her house straight to the well, right? That's one route that she could have taken, but she decided to go around the other route and then reach it. But do you realize, guys, moving from her house to the well is the resultant, it's the same effect as moving from her house to Precious's house to going to the well. So if I add the distance that she has moved, if I add the vector that she has taken to move to Precious's house, then the vector to move that is going to be equal to just moving straight from point A to point B. So basically that's how the vector method is going to work. So it's going to work like this. For example, you have a vector like this, right? Then you say this is vector A. Then you have another vector like this. Let's just say this is a vector B. Then if you join them head to tail, so you're going to take the head of this vector and join it to the tail of that other vector. So we're basically going to take this vector. So let's take it as it is, right? Vector B. Okay. Then after we have vector B, okay, let's take vector B. Okay, okay, so you have vector B over here, right? Then we're gonna take vector A, right? Vector A as it is, and we're gonna join it head to tail. So we're gonna take vector A, and this time, okay, so as you can see, I hope you're following. We're gonna take vector A, and now what are we gonna do with vector A? We're gonna connect this vector to the tail of this vector. So it's called the head. This head, which is over here, right? This head is going to be connected to the tail, this tail of the other vector. So it's head to tail. You can't connect this head to this tail, to this other head. It doesn't make sense. So it's going to be this head to that tail, which is going to be over here. You're going to leave it like that, right? Your resultant vector is going to be from the tail of one vector, which is going to be tail from this, to reach the head of the other vector, something like this. So this is going to be your resultant, which is the same as Sarah moving from her house to the well, and she has taken a route where she has gone to see Precious over here, and then she has returned to the well. So it's basically how you can add vectors. Take the head of one vector, connect it to the tail of the other vector, then the resultant is from the tail of one vector to the head of the other vector. So there's going to be the head to tail method, and we're really going to use it in depth. Another method that we're going to use is the parallelogram method, and I'm really going to use these methods when I'm solving past papers, so they can really be able to understand how we can be able to find, at times they can ask you to find the resultant of vector. And the last part that we're going to talk about is going to be vector resolution, and we'll be closing off the topic of physical quantities and units, and we're obviously going to solve tons and tons of past papers, but we're going to talk about vector resolution first before we reach to that. So vector resolution is basically going to be about you have a vector, and you want to resolve the vector into what we call components, the components of that vector, right? So how this works is you have a vector that you have, right? So let's assume you have something like this. Okay, you have this vector, right? Okay, let me use another thing. Okay, so with vector resolution is you're going to take your vector over here, right? So you're going to have this vector, right? Let's put it over here. And you're going to have a vector that we call that is inclined at an angle. That's the whole point of vector resolution. It is the process of splitting a vector into its non-components, which are both, number one is vertical components, and number two is going to be horizontal components. So we're going to have a vector that is inclined at an angle. So it's going to be something like this. A vector that is at an angle, right? Something like that. And we're going to basically, okay, we're going to take this vector, right? Something like this. Okay, let's put it over there. Right, so it's inclined at an angle. And we're going to say that angle is theta, right? So this is an angle theta, okay? So we're going to resolve this vector u into two components, right? And if you're familiar with trigonometric ratios, if you're not, I'm showing them on the screen right now. We have what we call the cosine rule, where we say cos theta is actually equivalent to the adjacent divided by the hypotenuse, right? So it's the adjacent divided by the hypotenuse. Then we say that tan theta, right? So it's the adjacent divided by the hypotenuse. Sorry for the spelling. Hypotenuse. Okay. Then we also have sine theta, which is going to be the opposite, right? Divided by, again, the hypotenuse, right? So basically, cos theta and sine theta are what we call trigonometric ratios, right? So you can resolve a vector into two components, where this is going to be your adjacent, right? Your adjacent, and this is going to be your hypotenuse. So this is going to be your hypotenuse. So what does this mean? It means that for you to get an adjacent, it's going to be cos theta multiplied by the hypotenuse. So if you're going to resolve this, it's going to give you, this side is going to be u cos theta. And this one is going to be, for this angle, this is going to be the same. So this one going up here, it's the same again as going from this direction going up here. It's just the same thing, right? So for this one, this is going to be the opposite. So if you're going to deal with the opposite is going to be, again, sine theta, right? Sine theta times the hypotenuse. So you're going to have u sine theta. So you're going to have u sine theta to represent this component. You're going to have u cos theta to represent this component. So that's basically the whole process of vector resolution. You have a vector and you resolve it into two components. U cos theta, which is like you move down, and the u sine theta, which is like you move away from that angle. One trick that I learned, which was really very helpful in understanding this particular thing, was that whenever you're given a vector, I'll give you the example right now, was that whenever you're given whenever you're given an angle, like, so you have something like this, right? This is how it works. And then you have something like this, okay? Then you have something inclined at a specific angle, right? And let's say that angle is theta, right? That thing is inclined at a specific angle theta, right? And this is your angle theta. And you've been asked to resolve the components, which is u, right? You've been asked to resolve the components, right? So how you look at this is you're going to start at the point which is over here. So you have two sides. You want to determine, is this cos, is this one a cos, or is this one going to be sine, right? So sine is more like sin, right? So from church, people know that you turn away from your sins, right? So if you turn away from the angle, you turn away from your... So that is the whole process of vector resolution, so that you can be really able to understand if you're going to turn away from the angle, you're going to arrive at sine, so it's going to be u sine theta. And if you're going to close the angle, that's going to be cos, you're going to arrive at u cos theta. I hope it makes sense, guys. And I hope you understood what vectors are and scalars are. And I'll meet you in the next video. We'll be solving specific questions on vectors and scalars. Thank you guys for watching, and I'll see you in the next one.